Okay, LP3. Um, oops. So we are in the XY plane. And we are trying to find a line. The equation of a line passes through the point 5, 6. Here's the point 5, 6, let's say. And it's perpendicular to the vector 3, 2. So 3, 2 maybe is about like that. So the line that I'm looking for is a line like that. There's our normal vector. There's our line. There's our normal vector. Okay, does that make sense? Everybody on board? So this is I'm going to call this x naught because we're going to use it as the x naught. This is 5, 6, and the normal vector here is 3, 2. Okay. All right, so how do we find the equation of the line? Well, beautifully, when you want to find the equation of the line, it's always going to be the same. It's always n dot x equals n dot x naught. The only challenge is to figure out, what's that normal vector, and what's the x naught. And in this problem, these are actually given, right? The normal vector, the problem said that this 3, 2 vector is perpendicular to the line. Right. So I'm going to use that as my normal vector. Sweet. This given that this point 5, 6 is on the line, therefore I can use it as my x naught. So my equation of my line, I get to instantly simplify this as 3, 2 dot xy equals 3, 2 dot 5, 6. And so therefore 3x plus 2y equals, okay, let's see, 15 plus 12 is 27. There we go.
But that's the equation of the plane containing the line.
This is the equation of a line in R2. So the problem is, this problem takes place in R2. Notice that the points are all given with just 2 coordinates. Yeah. So if the problem is in R3, now you've got a valid complaint, a valid confusion. If it's a 3-dimensional problem where there are 3 different variables running around, then you're right. This would be 3x plus 2y plus 0z equals 27, and this would be the equation of a plane. But that's not what we're dealing with. This is not a 3-dimensional problem. The problem is the problem here is a line in the xy plane. It says right here, xy plane.
All right.
So it's intrinsically a 2-dimensional problem, and in the xy plane, this is the equation of a line. And this is the equation of a line. Yeah. Yep. Does that make sense?
Yeah. But, okay, what if you say that because the direction vector of a line could be, like, there could be many, many different direction vectors?
Well, many in a certain sense. You could have, here's a different possible normal vector, right? Here's a different possible normal vector. You're right, there's lots of different potential normal vectors. Do notice that they are all parallel to each other, right? Yeah, because lines in R2 have this feature that there's really only kind of, I'm going to say, sort of one direction that's perpendicular to that line, because there's only sort of one dimension left. And likewise with planes. If you have a plane in R3, maybe that's the the normal vector, or wait, maybe that's the normal vector, or maybe maybe that's the normal vector. But all these possible normal vectors, all these vectors that are perpendicular to the plane, note they are all parallel to each other.
So equation of a line in 2 dimensions is the same as the equation of that plane?
Well, the equation of a line in 2 dimensions has the same sort of dot product structure as the equation of a plane in R3. That's right. And so this is in the book back here. Let me just flip back here real quick. So here's the equation of a plane, right? And you're right that looks practically exactly like the equation of a line in R2. But the critical difference here is that these are two-dimensional vectors, right? And so even though it algebraically sort of, notationally looks the same, these here are three-dimensional vectors. So it's kind of technically a different equation because these vectors are of different dimensions because the problem is living in a different world. Yeah. Yes.
So if all of the normal vectors are pretty much parallel to each other, you say like find two unit vectors are like going to be the same.
They're going to be parallel to whatever, like if you want to I think it's a different exercise, isn't it?
Well, yeah,
is that right?
I had a question about it.
Yeah. No, that's a great question. Let me make that as a separate answer. But yeah, that's right. So let me relate this back to what we were doing here on the recording here. So you're right that we could have chosen different normal vectors here. So I chose 3, 2 because, well, I'm given that vector is perpendicular to the line. But I could instead have chosen, let's say, M is 6, 4. And I could have written down 6, 4 dot xy equals 6, 4 dot 5, 6. And when you multiply that all out, what you get is 6x plus 4y is equal to 54. And what you notice is that they're not exactly the same equation, but one is just 2 times the other one. So they're logically identical. This one is just 2 times that one. So morally, they're kind of the same equation. Yeah. So using different normal vectors doesn't make any difference. Okay, let me stop this recording and I'll move on to the next question. Hang on just a second.